Hello, my name is Amina Powell. I'm a medical physicist, and today I'm going to talk to you about nuclear medicine. My talk will discuss my career path, about how I became a medical physicist. I'll then talk about what goes on in a nuclear medicine department, for example, the kind of studies that we do, and then I'll talk about the physicist's role within nuclear medicine. So first, a little bit about me. I'm a registered clinical scientist and I completed my training last year. My current role is a nuclear medicine physicist and I'm based at the Royal Brampton Hospital, which is in Chelsea, London. So at school, I really enjoyed the sciences. So for A-levels, I chose physics, maths and chemistry. And it was during this time that I did some work experience at my local medical physics department and decided this is the area that I'd like to work in. So for my degree, I enrolled at the University of Liverpool and did a course which was physics with medical applications. And then after I graduated, I stayed at the University of Liverpool and completed a nuclear physics PhD. It was after this that I then enrolled onto the scientist training program. So you do need a physics degree or a closely related degree to apply for this program. It's supported by the National School of Healthcare Science. It's a 3-year program of work-based learning. So I did mine at Leicester Hospital and then completed my training at the Royal Brampton Hospital, which is where I still am now. During the course, you also get a university accredited master's degree, and there's 4 specialisms. I decided to specialise in imaging with ionising radiation, and that covers both nuclear medicine and diagnostic radiology, which is like X-rays and CTs. But there was also options to specialise in radiotherapy, radiation protection, imaging with non-ionising radiation, and this covers things like MRI, lasers, and ultrasound. So what happens in a nuclear medicine department? So in a nuclear medicine department, we administer small amounts of radiation to the patient via an injection or sometimes through radioactive capsules the patient will swallow. So when a patient is sent to us for imaging, we trace the radiation distribution with cameras to see how processes inside the body are functioning. One of our cameras is shown here, and how this would work is a patient would lie down on the couch after they've had their injection. The couch will move through these 2D camera heads, and these camera heads rotate around the patient. They detect the radiation that is being emitted from the patient and build up a 3D image, which can be sent for diagnosis. And then another reason why a patient might be administered radiation is for therapeutic purposes, and this is where the radiation is used to destroy cancer cells. And I'll give an example of an imaging investigation and a therapeutic treatment we do in a couple of slides' time. But first, we'll just have a quick recap on radiation. So unstable atoms are atoms that have an unbalanced number of protons and neutrons. Now, unstable atoms will want to attain stability, so they'll do this by emitting radiation. So there's 3 different types of radiation that can be emitted, either an alpha, beta, or gamma rays. So alpha radiation is what we call a particulate radiation. It's essentially a helium nucleus and it has 2 protons and 2 neutrons bound together. The general equation for alpha decay is shown here on the slide. Alpha radiation is strongly ionizing. It's also the least penetrating of the radiation types and can be absorbed by a sheet of paper. Beta radiation is essentially a fast-moving electron. It can transverse through paper, but can be absorbed by foil or perspex. Gamma rays are higher energy electromagnetic photons. They're emitted when an excited nuclei moves to a lower energy level. The release of a gamma ray will not change the number or types of particles present in the nucleus. I've included again on the slide the general equation for a gamma ray decay. As you can see, the asterisk normally is associated with an atom being in an excited state, but the number or types of particle present within the nucleus, so the A atomic number and the proton number stays the same. Gamma rays are the least ionizing, but they are the most penetrating and can be absorbed by lead. But depending on the energy of the gamma ray depends on the thickness of lead that you would need to absorb gamma rays. So radioactive decay is a random process. If we have a sample, we can't predict when a decay will occur. But what we can describe is the activity of the sample, and that is the number of decays that we can measure each second. Activity has the unit becquerel, and 1 becquerel equals 1 disintegration per second. The activity of a sample reduces exponentially, so can be described by this equation here, where A is the activity after a certain time has passed. A0 is the original activity of a sample, and minus lambda is the probability that a nucleus will decay per second. So lambda is related to half-life, and the half-life is the time taken for the activity of a sample to halve. And this is the equation that describes the relationship between half-life and lambda. So one of the studies that we do is called a myocardial perfusion imaging. And what this is basically is a study to test how well blood flows through the heart muscle. To do this, we administer a radioisotope called technetium, and this is a gamma ray emitter. And this will be taken up by the heart in the same way that blood would flow through the heart. It has a half-life of 6 hours, and in nuclear medicine imaging, we want our imaging radioisotopes to have a relatively short half-life, as we want the patient to only be radioactive for the duration of the scan, and we want their activity to fall away quickly after that, as we want the radiation dose of the patient to be as low as possible, and also the dose of those around them to be minimal. So for this investigation, the patient actually receives 2 separate radioisotope injections and has 2 sets of images performed. So for the first injection, they're given 200 megabecquerel of technetium, but they're also given a second drug which emulates the effects of exercise on the body. And then after this, they'll be sent for imaging. They'll come back later in the day and have a second injection of technetium of about 400 megabecquerel, and then be sent for a second set of images. So on the left here are the 2 set of images from a patient. So at the top there's the stress images, and what we do for a lot of our nuclear medicine images is we colour map them. So on this particular image, orange is indicative of areas where there is a large amount of technetium present, and hence where blood flow has occurred in the heart muscle, and areas of purple/green are areas of low uptake of technetium, and hence blood within the heart. So as you can see from our stress and rest images, it's quite similar intensity, and the blood flow has reached the heart muscle throughout quite well in both the stress and rest images. So this is a sign that the heart is quite healthy, that there's nothing untoward going on. On this second set of images, unfortunately, you can see on the stress images there are regions of lower uptake, which could be indicative of ischemia, which means blood flow isn't getting through to the heart muscle as it should. So once the consultant has viewed this for a patient, they can then work out a treatment plan, which could involve blood medicine, and in some cases surgery. So nuclear medicine departments will also support radionuclide therapy. So one of these therapies is called selective internal radiation therapy, SIRT, and this is used to treat tumours that are found within the liver, and especially these are for tumours that can't be removed surgically. So the radionuclide that we use for this is yttrium-90, which is a beta emitter, and it has a half-life of 2.7 days. So beta emitters are good for therapeutic purposes because they have a short range and they're absorbed easily. For the betas from yttrium-90, they'll have a range maximum of 11 millimeters within tissue and a mean range of 2.5 millimeters. We administer a maximum of 1 to 3 gigabecquerel for this therapy. So the yttrium-90 is actually delivered within microspheres, which are made out of either resin or glass. Now these microspheres are very tiny, about 25 to 75 micrometers, and the reason for this is they get stuck, or they block the capillary tubes that are feeding the tumour with blood and then they can deliver a very localized dose to the cancer cells. So they're delivered in these resins via the hepatic artery, which actually supplies 90% of the blood to the tumor. So which is where the tumor derives 90% of its blood supply from. So by injecting it through this, you're getting directly to the tumor and you're helping cut off its blood supply and destroying the cells of the tumor. Whereas the healthy liver gets most of its blood supply from the portal vein. So after the patient has been administered these resins, later on that day, normally they might also be sent for a scan. So even though, as I said, beta particles will stay within the patient, due to an effect called bremsstrahlung, we have photons that are produced, and then we can use these to scan the patient. And this is one of the images here on the right hand side of the screen. As you can see, this is the CT on the right showing the liver, but on the left is the radionuclide image, and as you can see, via areas of red, which is high uptake of the radiation, the radiation dose is very localized, sparing a lot of the healthy liver, which is what we want to see. Another therapy that is supported by nuclear medicine is radium therapy. Now, this is used to target and destroy cancer cells that are in the bone. Normally, patients who are referred for radium therapy are patients who were primarily diagnosed with prostate cancer, but unfortunately the cancer cells have now spread to the bone. So the radionuclide used is radium, and it is an alpha emitter which has a half-life of 11.4 days. Radium behaves very similarly to calcium within the body, so it is absorbed readily by the bones, which is good. And because the alpha particles only travel a short distance, the cancer cells get a very high dose of radiation, which increases the chance of them being killed, whereas the healthy cells only get low dose or no radiation dose at all. This also means there are very few side effects from radium therapy. Radium therapy is delivered via an injection into the vein of the arm. Normally there are 6 injections of radium given to the patient in total, and these are given with a 4-week gap between each one. So I've spoken a little bit about what goes on in the nuclear medicine department. So now I'm just going to go through what a physicist's role is within the nuclear medicine department. So a large part of our role is to ensure radiation exposure to staff and patients is as low as reasonably practicable. We ensure that there's correct shielding available for staff when handling radiation. For example, lead and tungsten syringe shields, which help minimise the dose to the technologist's fingers when they are injecting the patient. We have lead screens within the camera rooms, because as the patient is radioactive, they are a source of radiation. So while they're on the couch getting scanned, the technologist can sit behind these screens and their radiation exposure is minimized. We are also in charge of the dose monitoring program for staff in the department. So the way this works is that the physicists will hand out radiation badges, which are worn by all the staff in the department. These are then collected and sent for analysis, and they give a monthly total of the dose a staff member has received, and physics will look at these results and make sure they're within the legal limits and put in any actions that might need to be required if we see doses increasing higher than they should be, or an increasing trend where this could be prevented. We also optimize imaging and therapy protocols to make sure they're the most efficient, and we also help clear up any radioactive spills that might occur in the department. And we also write and review the risk assessments for each of our procedures that take place within the department, and local rules, which all staff members have to sign and abide by while they're in the department. Another large part of our role is ensuring that equipment is working correctly and safely. So we test a lot of equipment that is within the department. So for example, gamma cameras, we do monthly and 6 monthly tests on these. Gamma cameras are used to trace the radiation within the patient to provide an image. So it's important these are working correctly. Also, contamination monitors. These are used to detect radiation that may have spilled and helps us when we have to clear up any radioactive spills that have occurred. Another piece of important equipment is the radionuclide calibrator. So a radionuclide calibrator is used to measure the activity of a radiopharmaceutical before it is delivered to a patient. This means it is extremely important that it is working correctly. There are daily checks on the radionuclide calibrator by technologists, and monthly and annual checks are made by physicists. One of the annual tests that we do is to ensure the calibrator is measuring activity linearly over a range of activities that are used clinically. So the range that we normally test the calibrator was linear for, it was from 3 gigabecquerels down to 3 megabecquerels of activity. So the way that we do this linear check is that we have a vial of technetium, which is the isotope that is most commonly used in nuclear medicine, and we place this vial, which as I mentioned would contain about 3 gigabecquerels of activity, within the radionuclide calibrator, and we measure the activity of the vial every hour over 3 working days. Now, using the first activity measurement that we noted down, we predict using the radioactive decay equation what the activity should be at the different times that we have measurements for. And then what we do is we check that the calculated value is within 5% of difference of the measured value. And if this is the case, then the calibrator has passed its test. So within this presentation, we have covered the different types of radiation, how radiation is used within a nuclear medicine department, and the role of a nuclear medicine physicist. I hope you found this useful, and good luck with your exams and the rest of your studies.